All right, test. Okay, cool. All right, I think the mic is on. And yeah, thanks everyone for coming to this session around how to save money on your serverless architecture. So my name's Yan. I've been building stuff on AWS since about 2010. Initially, obviously, everything's done on EC2. And then when containers came around, I went on the whole containerization journey. And since about 2016, I've been pretty much entirely focused around the serverless. And nowadays, I wear a couple of hats. Part of my job is working with the Lumigo team, which I still think is the best observability platform, especially for serverless workloads, and help them with developer advocacy. But the other half of my time, I also work as an independent consultant, where I work with other companies and help them adopt serverless and avoid all the problems and mistakes that I've made along my journey. And one of the things I like to do as a consultant also is along the way, I like to collect ideas and tips on how to build more cost-efficient systems on AWS. And so I hope you like drinking from the fire hose, because I've got quite a few different things I want to throw at you. And hopefully, at least some of them will stick, and you can take away and go back to work and start using them right away. So start nice and simple. I think something that most of you should be aware of already if you're using AWS. And I think this is something, billing alarms is something that everyone should have. Maybe it should even be the first thing you do when you open an AWS account is to create your billing alarms. They're not perfect by any means. They are usually, I think, about 4 or 8 hours behind the real time, but it's much better to find out that you've got a problem happening and brewing a few hours late than, say, a few days or a few weeks late. That's a good example I found from a good friend of mine, Luke, who is a principal engineer at PostNL, and they are the National Postal Service in the Netherlands. So what happened to them was they pushed out a one-liner change, and then a few days later, they got an email from the AWS billing alarm that they've crossed their $2,000 monthly budget that they've set ahead of time. So what happened to them was actually they just make a one-liner change to one of their Lambda functions, which broke caching. So instead of calling secrets manager and fetch a secret at cold start and then caching it, they are making a call to secret manager on every single Lambda invocation. And when you are the National Postal Service, you're going to have a lot of events you have to process. So for them, this was literally going from a few hundred requests to secrets manager to billions of requests. And when you charge, I think, something like $10 or something like that per million requests, those costs can quickly build up. As you can see, they made a code change around there, and suddenly, straight away, you can see those increases on the billing. So the moral of the story is that yes, billing alarms are a few hours behind, but when you have something like their team there, their threshold is fairly high because their usage is actually fairly high based on the workload they are doing. But having those billing alarm in place just means that you find out there's a problem before it goes even further, when it becomes much worse. The last thing you want is for your CFO, your chief financial officer, to come to your office and knock on your door and goes, "Hey guys, I noticed something. Your bill went from a few $100s to $10,000, $15,000 a month. What happened? What did you do?" So avoid those embarrassment and just have the billing alarms as your safety net. When it comes to cost, especially around the serverless environment, I find that the number one cost I often find in my customers' bills is CloudWatch. Much more so than your Lambda function costs or your API gateway or even your database costs. You often find that the CloudWatch is the number one or number two item on a customer's bill. And the worst thing is that the more data you collect, the more logs you collect, the less value you're going to get, because you now have got this much bigger haystack you have to log through every time there's a problem. You get an alert. You want to figure out what was the problem. Now you have a harder time to find the issue because there's so much data you have to chance through. So there's a couple of things I like to do to keep my CloudWatch logs cost under control. Number one is doing structured logging. It's surprising to me how many people are still not doing that today. So every time you want to log a message, you want to think very carefully, what does this message tell you? How are you going to use it? Is it for just simple debugging? Is it general information about initialization and things like that? Or if it's an error, but you can handle it, you can just move on, then it's a warning because it's not stopping you from processing the user request. But if it's something that you can't handle, you have to just error out and blow up, then you have to log that as an error. Luckily, with Lambda, when it comes to error handling, even if a single user request blows up your code for some reason, it's not going to impact other users because individual user requests are handled by different execution environments. So one of the nice things about working with Lambda is that you get better resiliency just from the fact that you have this isolated execution environment where you don't have a case where, say, one user request blows up the server, and suddenly all the other 100 concurrent requests being handled by the same server also dies as well. So you think very carefully about what each message you're logging is going to do, and then in production, you set your minimum log level so that you're not capturing every single log messages. So most of the debug log messages, you don't really need them. In production, you have so much traffic, ideally, that a lot of the information is just not useful when it comes to successful requests that you are handling. Most of the time, it's fine, so I don't need to know exactly what happened to a very fine-grained detail. You also don't want to be in a situation where in production you have no debug logs, because when there is a problem, they are still very useful for debugging. So what you want to do instead is have some kind of sampling in place, and you can do this different ways. One way is to use the Lambda Power Tools from AWS, which has got some capability to let you do some sampling with your logger, such that, say, you will enable debug logging for 5–10% of the invocations, but for the other 95% of the cases, you just only log at the info level. That way, you always have some body of debug logs so that when there is a problem, you can use them to help you debug the issue. Another thing to keep in mind is that when it comes to CloudWatch logs, the default retention is never expire, which means, well, AWS doesn't want to delete your data without you saying so. But it also means that now you're going to be paying 3 cents per gigabyte of data forever because you never clean up anything. And when it comes to logs, they lose their value pretty quickly. The logs from, say, 2 months ago is pretty much useless when it comes to debugging. So what you want to do is to change those retention period to something more reasonable, like 14 days or 30 days. Because you do pay for those data storage costs, even though by comparison, your biggest cost when it comes to CloudWatch is around the data ingestion. So how much data you're ingesting? You're paying 50 cents per gigabyte. And one thing I see a lot with customers is that, well, they don't actually like to use CloudWatch to query the data because there's some support for cross-account, but then when you've got lots of accounts, using resource assets management to resource sharing, or using RAM to sharing access to CloudWatch logs is quite clumsy, especially when you have a scale across hundreds or AWS accounts. So what I often find is that someone would set up something like that, whereby Lambda captures your logs automatically, sends them to CloudWatch logs, and then you have a Lambda function to then shuffle those logs to some third-party vendor you actually want to use, because maybe they've got a better UI for it, maybe they have an easier way for you to access all of your organization's logs, not just, say, logs for one particular account. The problem with this kind of setup is that, well, you're still paying for CloudWatch to ingest the data in the first place, and then you are also then paying a third-party vendor a second time to ingest the same data and then to store them as well. I don't mind spending money on my system, but I do want to make sure that every penny I'm spending, I'm getting some return on investment. And double paying for the same logs for processing and storing them is not good value for money. Nowadays, you've got a better way to do this when it comes to Lambda through the Lambda extensions mechanism, which is a way for you to run a sidecar next to your main function module, your main process that runs your application code. So this allows you to run something on the side from your main application, and then you can use the telemetry API, which is a local API that you can access in the Lambda execution environment that allows you to subscribe to telemetry events, like there's a new log event or a telemetry metrics that you can that's been generated by the system. And then what you can do is that from that sidecar, that Lambda extension, you send it straight to the third-party vendor. This, however, doesn't stop Lambda from sending your standard out or standard error messages to CloudWatch. So what you want to do instead, well, on top of that, is you want to add this tiny block of permission to your Lambda function's IAM permissions so that it blocks the Lambda function's permission to send any data to CloudWatch logs. That way, you're only sending data, those logs, to the third-party vendor through your own Lambda extension, rather than paying for CloudWatch to ingest the data as well, and therefore you avoid double paying for the ingestion of the same logs. And if you want to have something that works better than CloudWatch logs, and that gives you ability to also treat your structured logs as events so that you can do more ad hoc, I guess, aggregation of those events so that you can turn those raw log events into custom metrics and alarms. Then also check out Lumigo as well. They have really good support for this, whereby you can send all of your structured logs and they will ingest them as JSON events. And you can be as wide as you want. You have as many fields as you want. And then on demand, you can aggregate them based on some query. It could be average of some latency you're tracking, or error count, status code, and things like that. And then you can create alarms against those custom metrics that you're creating at no extra cost. Whereas if you do this in CloudWatch, you can use the embedded metric format in CloudWatch to do the same thing, essentially. But then you're going to be paying for the log ingestion, you're going to be paying for the metric, and then the alarm separately. Whereas when it comes to Lumigo, you kind of pay for just the ingestion as opposed to paying for the different components separately. One more thing I want to touch on when it comes to CloudWatch log is the system messages. So when it comes to Lambda functions, every single invocation, you will have a number of log events from the system, including when it started, when you finished, how long it ran for, what was the duration you got billed for. So in this case, Lambda charges you per millisecond of execution time. For 99.9% of people, this is fine. There's not much data, so you're not going to pay a huge amount for it. However, when you're someone like Thafan Analytics, which does web analytics, they track millions or billions of events every month. And for them, just those system messages alone was costing them like over $1,000 per month. And they're not getting any value for it. So when you have system messages for Lambda that you're not getting any value and you're paying a non-trivial amount of money for it, then it's better to consider using the new, relatively new, I guess it's been about 2 years now, the Lambda's advanced logging controls, which allows you to configure on your Lambda function, and you can do this both through the CLI, SDK, as well as any infrastructure as code tool, a log format. So this setting allows you to say, for my Lambda function, whatever I'm writing to send it out, by default, is going to be treated as a text message. But you can say, OK, my system wants to have structured logging, so please wrap my message into a kind of like a simple JSON structure. So this way, it kind of gives you that structured logging without you having to change all of your application code to write structured logs. It's kind of annoying that they kind of tie two things together, because once you set the log format to JSON, it also then allows you to configure a system log level to say which of the system messages do I want to see in the logs. And if you just want to see when there's unhandled exceptions that blows up your process, then you can just set the system log level to 1, so you don't see any of those start and report messages just when you have unhandled exceptions, which maybe just that's all you care about. You don't care about all the other system messages that you get from Lambda. And staying with Lambda, probably the number one way to optimize the actual cost of Lambda function itself is by right-sizing the memory setting. Because when it comes to Lambda, the more memory you allocate, you get more CPU resources as well as more network bandwidth as well. They give you a single thing to control the power and the cost for your function. So you can easily go from just 128 meg all the way to 10 gig. And one interesting detail to remember here is that every 1.8 gig of memory allocated to the function, it unlocks the second CPU core. So by the time you have a 10 gig of memory to the function, you actually have 6 virtual CPU core rather than one really, really powerful one. Which also means that to take full advantage of the amount of memory you're allocating, assuming that you are allocating more memory to get more CPU, you have to write your code to be able to take advantage of multi-core. And it's very easy to get this setting wrong by order of magnitude and suddenly spending way more money on Lambda than you really need to. For most people, this, again, not something that I typically see in the wild, But I have seen one customer who had run into problem with this. So this is a customer who was doing video rendering with Lambda, and they were using Node.js to do a lot of the, you've probably seen those on YouTube where it's like a hand-drawn animation style video. They got some kind of script going on. And so they had a system for automating a lot of these things for the customers. And one day I got a call from them and said, hey, Yan, can you come in and help us out? Because our Lambda function cost just suddenly blow up. And it went from, I think, a few thousand, well, like $1,000 or under to $10,000. So when I came in, I realized that like 99% of that cost was going to one single function. That's the function that does the rendering. So it's doing some CPU-intensive work. And it was set to have 10 gig of memory. And I spoke to the team. They told me, oh, yeah, we knew that the more memory equals more CPU, so we want to get this rendering going faster. So we maxed the CPU allocation. What they didn't think about was the multi-core factor, because the code was written in JavaScript, and JavaScript runs on a single-threaded event loop by default. So unless you're using things like threads or worker, you're not able to actually take full advantage of the 6 CPU core you have, which means even though they're paying for 10 gig, they're only really using 1.8 gig of those memory in terms of the CPU resources you get. So for us, the quick fix was go all the way back down to 1.8 gig and then refactor your code to actually take advantage of the multi-core you have. Then you can go back to 10 gig. Again, doesn't matter, well, it's fine to spend money, but I don't want to waste money on things I'm not getting any value for. And once you go to, say, multi-core solution, then you can actually render 6 times faster, so your cost will stay the same. So higher cost per millisecond, but a shorter time means that you're roughly spending the same amount of money. But you're getting a faster rendering time. Unfortunately for them, because they were only using 1 core out of 6, so they were paying more, but not getting any value for it. I think we all know this quote that from McDonald Knuth that 97% of the time, premature optimization is the root of all evil. But I think the second part probably doesn't get as much attention, that whenever we find that critical 3%, that's where we really want to hone in and make sure that we optimize the hell out of our application and get the most performance we can. And when it comes to serverless and Lambda, Lumigo has got a really nice dashboard that allows you to sort your functions across your entire account by, probably can't really see very well, by memory use, but also by estimated cost as well. So for most customers, I see maybe 1 or 2 functions account for most of the Lambda cost. So it's very easy for you to find those outliers, that's 3%, so you know exactly where you want to optimize in terms of improving your cost efficiency. And so with this, you can very quickly find out which functions you want to right-size. And when it comes to right-sizing the memory setting for your Lambda function, there's a really good tool, again, from AWS employee. You can Google it and look for Lambda Power Tuning Tool, which is essentially a step function state machine that takes your function, creates multiple variants of it, one for 128 meg, one with 500 meg, one with 1 gig, 2 gigs, 3 gig, and so on. And then you will invoke each of those variants 100 times by default. You can change this, and so that you can measure in terms of the cost. How does it change as you add more memory to your function, but also in terms of the performance, so that the more memory, the faster it goes. But as you can see, with this function, over 1.8 gig, you just don't see any improvement anymore because it's single core. But then if you see the cost efficiency, initially, adding more memory actually means you spend less. Higher cost per millisecond, but running faster means overall you can spend less. Until that's not true anymore, whereby by adding more memory, you're not getting the full CPU power because you're not writing your code to take advantage of multi-core, then your cost will go up, but your performance is not going to make it's not going to improve. Another thing to consider when it comes to Lambda and the cost efficiency is that Lambda supports both x86 and ARM. And per millisecond, ARM is cheaper, about 25% cheaper than x86, which is great. But your performance may differ on ARM versus x86. When AWS launched this ARM support, the blog post said they had something like 25% cheaper per millisecond, plus another like 15% faster performance. So overall, they were quoting something like 40% more cost efficient. However, when I tested on most of my functions, I found that ARM was slower. Sometimes on one of my functions, I forgot what it was doing. It was something like 6 times slower than x86. Same code, no change. Switch to ARM, suddenly 6 times slower. So 25% cheaper per millisecond, but 6 times longer, runs longer, then overall you're spending a lot more for that same function to run on ARM than it is on x86. But where I find this actually really useful, a really good way to just save some quick money on Lambda, is when you've got functions that has got a lot of, dependencies you have to call, and you spend a lot of time just waiting for that response. And this happened to me in a project where we did a lot of integration with Salesforce. And the Salesforce API, I'm telling you, sometimes they take like 50 seconds on average to respond, which means I'm paying for my function for every single millisecond, and it's going to spend every time it calls, it runs, it spends 50 seconds just waiting for Salesforce to respond, which is horrendous. So for cases like that, unfortunately, we couldn't do anything. We had to use Salesforce. So I was stuck with finding some way to optimize it a little bit. And so ARM was very good to say, you know what, we can't really do much with the response time from Salesforce, but let's just take that 25% saving by using ARM for this single function. Again, it's not CPU-intensive work, so performance didn't really differ very much. So we just take that saving from ARM and, pay for the idle time, unfortunately. Again, staying with Lambda, there's probably the single biggest anti-pattern I see quite often is having synchronous Lambda invocations. So when it comes to Lambda, there's basically every time you want your function to run, you have to go through the invoke API. And there's a very important setting here called the invocation type. So you can either invoke a function synchronously by setting this invocation type to request response, in which case the Lambda API you're calling, the invoke API you're calling, it's not going to respond until the function has finished running. So it gives you back the output as the result. So that way your code has to just wait and wait for the function to finish. But you can also invoke the function asynchronously by setting invocation type to event, in which case the Lambda API is going to respond straight away. And then the function is going to run behind the scenes so internally there's like a SQS queue in the Lambda service. So for async invocations, it's going to put that request onto the internal queue, and then it's going to invoke it later. One interesting, thing that comes from that is that when it comes to async invocations, Lambda functions will never throttle you. Even if your function doesn't have enough concurrency available, the Lambda service will still say, yep, everything's fine, because at that point, all it's doing is putting the request on the queue. And then internally, when it calls the function synchronously later on, that's when it enforces the concurrency control you have in place. Okay, so async versus the synchronous invocations, very, very different. And specifically, when it comes to synchronous invocations, I've seen this quite a lot, where, say, instead of having like a proper microservice design with boundaries and HTTP APIs, you have just Lambda functions dotted around, and the people just calling one function from another as if this is all just microservices. And this is pretty much always a bad design. There's maybe like 1 or 2 very, very specific use cases where this is a legitimate use, but most of the time it's a bad design. And oftentimes this happens within the team's service boundary. If you think about DDD and the domain and boundary context, so within a boundary of one domain, maybe even within one service, I often see this because people confusing Lambda functions, the infrastructure pieces, with Lambda functions in programming. So I've seen people go extreme, the distances whereby they encapsulate the function, the code at the Lambda function level, even though you can still have code level modularity. You don't have to put that all in the infrastructure, right? So if you have this inside the same service, just get rid of a second function and do everything in one function instead. Again, you can still have code level modularity and then infrastructure level modularity. They don't have to be all done at the infrastructure level. What about if you have service-to-service calls, cross-service boundaries, and you have different Lambda functions representing different microservices? Because, again, I hear this very often. Lambda functions are independently scalable, they're independently deployable, and they can be independently rolled back, and therefore every single Lambda function is a microservice, because if it quacks like a duck, it walks like a duck, it's a duck. But unfortunately, in this case, it's wrong. Microservice is not just defined by whether or not something is independently scalable and deployable or not. It's defined by what it's doing, the boundary context around that of that service, and what it's supposed to do. And in this case, when you have when you're exposing capabilities in your service to other teams to call as a Lambda function, what you're doing is that you're coupling those downstream teams to implementation details they shouldn't have to know about or care about. The fact that you're using Lambda to begin with, the fact that you're running in this account, this particular region, your function is called hello world. Those are all things that you should be able to change without having to force your caller to also have to change their code as well. So if you're going to expose some capabilities for other teams to use, just give them a good old regular HTTP API. So today you're using Lambda, tomorrow maybe you're running really high throughput because you didn't think this thing is going to be popular, and then it becomes popular. Then you can take the same code, move it to run in the container in, say, Fargate. And when you make that change, your caller doesn't care because it's all implementation details that they are not coupled to. So when you have to service calls, just do the simple thing. Just give them HTTP API they can call, and then behind the scenes, you can change things as you need to. So that is why synchronous Lambda-to-Lambda calls are like bad ideas. But what about asynchronous Lambda-to-Lambda invocations? I found a couple of use cases where this is actually quite useful. For example, if I've got a user-facing API, again, behind some HTTP interface that someone can use, I've got my Lambda function. In this case, is doing the thing that the customer wants, which could be save my user profile update. So that function will take your request and save it into the database to persist it. But there's also things that we care about as a system, as a business. We want to track your user action, maybe in like Facebook tracking, pixel tracking, what have you. Well, those things we want to do, but then we shouldn't ask you to wait for us to do that thing before we can respond to your request. So what I can do instead is that I can take those secondary responsibilities and put into a second function, and I will invoke that second function asynchronously, so the request comes back straight away, and then it gets run behind the scenes. And this way, I can improve user experience because the first function can respond to you quicker and reducing that user-facing latency, but also importantly as well, that allows me to build more robust error handling. Because now I don't have to worry about the actual user-facing latency while I do retries and exponential backoff, and the user is waiting for the response for the thing that we said we're going to do for them. But also with Lambda's async invocations, you get 2 built-in retries from the service, but also you get support for delta queue and Lambda destinations, so that when there's a problem, you can capture the thing that you try to do and failed, so that you can then retry them later through a separate process. And that's with the assumption that both functions are in the same service. So again, you don't want to make these async Lambda-to-Lambda calls across service boundaries, because again, on the other side, the other service, I shouldn't have to worry about or think about what Lambda function I'm calling or the fact that they're using Lambda functions at all. So as far as async Lambda-to-Lambda invocations are concerned, sometimes they're okay, depending on your specific use case. But I think a good rule of thumb to have is to always look at your architecture and ask, does every single component in this architecture exist for some reason? Am I getting some return on investment? Otherwise, can I simplify things and remove some pieces from my architecture diagram and my actual architecture as well? Because again, if you've got 2 functions that can be combined into one for that synchronous Lambda-to-Lambda call situation, just do it and simplify your code and your infrastructure. And then caching. So for me, caching is almost like a cheat code for building scalable and cost-efficient and performance systems. And if you look at your kind of typical serverless API, where you've got API gateway in front of Lambda, and you're using, say, DynamoDB for your database, and then in front of that, you've got CloudFront and the Route 53 and so on. There's so many different places to do caching. I always want to do some caching on the client side for things like static assets and for things like config files that doesn't change very often. But I also want to do some API response caching on the edge with CloudFront. That way, if everyone is calling the same API to get, I don't know, the profile image for someone's Twitter profile or LinkedIn profile, or what have you, again, I don't need to have to do that every single time. I can just cache that at the edge. But if I'm doing some CPU-intensive calculations, I also want to make sure that when a second time this function runs, I don't do the same calculation again. This can be, say, like a prompt to LLM, where everyone's asking the same question, and you've got a same prompt that you run for everybody. Instead of doing that every single time and paying for the LLM usage, you can just cache the response from the first time you ran that. So you can have application-level caching in your Lambda function, and then store them in some kind of distributed cache. AWS has the Elastic Cache service you can use, and it supports Memcache and Valkey or Redis now. But the thing I have against the Elastic Cache is that it's paying per uptime. I have this really thing against the paying for uptime and paying for wastage, because if no one's using my system, I don't want to be paying for that. So nowadays, I kind of prefer to use the Memento, a third-party service, really good serverless caching solution, whereby you only pay for the messages you're sending, the data you're saving. You're not paying for uptime for the nodes. So that way, I can have a whole system or just paying by usage, so that I don't have to worry about having different environments, which is, again, very powerful practice when it comes to serverless, using ephemeral environments. So I can take my system, I can create multiple copies, so that different developers can work on the same code base at the same time, but have different environments dedicated to them, so they don't have to worry about, deploying a change and overriding dev so that someone else can't run the test and so on. And you can take the same pattern and then take it up a further level to then have a cell-based architecture, which is a very powerful pattern that AWS uses internally for most of the services, whereby you have a multi-tenant situation, and you can put different tenants into different copies of your application, such that if one tenant is suddenly going from 10 requests per second to doing 1 million requests per second, you limit the blast radius of what single tenant can do to affect their neighbors. So cell-based architecture, really powerful pattern that we're seeing more and more now in the wild. And being able to set up your infrastructure as code to support the ability to create copies of your application, to create different environments easily, is a very powerful, really powerful pattern. And having services that are charging you based on usage only, not by uptime, makes it really easy for you to then have all these different copies of your environments without having to worry about paying for uptime multiple times. And that brings us to the last thing I want to talk about, which is choosing the right service to use. Because in the cloud, every decision you make essentially is a buying decision, right? AWS or any cloud vendor is like this giant candy store. You walk in with 100 different services. Many of them do similar things, but they maybe charge you differently, or maybe they have slightly different quirks. And every time you decide to use a service, you're making a decision to pay for that service. So it's a buying decision. And very often, choosing the wrong service to use can be very, very costly, because they charge you on different dimensions, and for different situations, they can manifest in very, very differently in terms of your cost. So if you're building some kind of event-driven architecture, you want to have some kind of a messaging service to ingest events and then to distribute it to somewhere else to process. So just a couple of services you can use for this in AWS. You've got your SQS, SNS, Kinesis. They kind of optimize for different workloads, but oftentimes they can be used interchangeably for simple use cases. 1 request per second, this is kind of what you're looking at in terms of monthly cost. But if you think, now we're doing 1,000 requests per second, suddenly things look very different. At a small scale, because Kinesis charges you based on uptime for the nodes, for the shards and streams, so it's more expensive at low throughput. But once you get to really high throughput, then the Kinesis is much, much more cost efficient, because the cost of per million requests on Kinesis is a fraction of what you pay for per million requests against SNS, SQS, and EventBridge. So as large scale, Kinesis is one of the most cost-efficient ways to ingest large amounts of events on AWS. Same thing happens with building APIs. You can use API Gateway, which has got 2 flavors. You've got the REST API versus HTTP API, but you also have ALB as well. Again, optimized for slightly different things, but they can oftentimes be used interchangeably, especially when it comes to building serverless APIs. So 1 request per second, ALB is more expensive because there's the uptime cost element. But once you go to, say, 1,000 requests per second, suddenly ALB is much more cost efficient compared to API gateway. And again, another good rule of thumb to have on AWS, I guess in the cloud in general, is that services that charges you based on uptime tend to be an order of magnitude more cost efficient at scale. Okay, but you must always understand the specific cost dimensions of the services they're working with. Because the example I showed you earlier for API gateway versus ALB is based on the assumption that your payload is quite small, 1 kilobyte. One of the cost dimensions you get with ALB is that you are charged for LCU, the load balancer unit, and one of the dimensions is data processed. So what happens if you're loading large payloads for some reason? I don't know what it is you're sending, but if you've got some large amount of payload you're processing and you're averaging 1 megabyte per request, what do you think those numbers look like? Not pretty, that's what. Like the numbers are pretty crazy once you get to, once you think about the specific cost dimensions for maybe some more extreme use cases, right? But it doesn't have the 1 megabyte on average. It can be even just 100 kilobyte. It will still be quite a different picture compared to what we were looking at earlier when we were looking at ALB versus API gateway. So a couple of years ago, Werner gave us the frugal architect, where he gave us 7 different laws for the frugal architect to think about your architecture design, your system decisions, your design decisions. And I really like 2 of the rules. One is that architecture is a series of trade-offs. You're always trading off one thing versus another. And that also importantly, this is probably a more subtle law, that you want to design your systems whereby your cost dimension grows, or your cost grows along the same dimension as your revenue. So as you are generating more revenue, your cost also grows accordingly. You don't want to be in a situation where your revenue is not growing, but your cost is going up, right? That's how it puts you into a negative. I've built quite a few different real-time systems on AWS, and you have quite a few services on AWS where you can basically build serverless WebSockets with API gateway WebSockets or AppSync subscriptions or the new AppSync events API. You can also do that with IoT Core as well. They all charge you on 2 dimensions, the number of messages you send, but also connection time. So say I'm building like a social network and I've got more users and they're all connected to the WebSocket connection to find out when they've been mentioned or they've been DM'd or what have you. So more user, higher connection time, but that's not where I make money. My revenue grows along the line of engagement. The more engaged someone is, the more likely they're going to turn from a free user into a paying user. The more the more they're doing on the network, the more likely they're going to start paying. So I want my revenue to grow along the line of activity and engagement, not along the line of just connected and not doing anything. So the services we talked about earlier for WebSockets, they charge us for connection time and activity. And that's, again, why nowadays I actually prefer to use Memento topics, which is give you a nice way to build push notification from the back end to the front end via topics. And the great thing about them is that they only charge you based on activity, the amount of messages you're sending out, not for connection time. So once again, if I'm building a system and I want to make sure that my system's cost is going to grow along the same dimension as my revenue, which is in this case is based on activity, then I want to make sure I want to use services that gives me that cost dimension that I'm looking for. And speaking of picking cost-efficient services or partners that you want to use, anyone remember this? Happened maybe a couple months ago now. Social network kind of just blew up out of nowhere, went from a few hundred daily active users to like 500,000 daily active users, and immediately got slapped with like $100,000 bill from Vercel. Because Vercel, as you probably know, is built on top of AWS, and so they are putting a markup on the underlying AWS bill that the AWS cost they have. And specifically for Vercel functions, there's a 7x markup over the underlying Lambda cost, even though Vercel functions are built on top of Lambda. And so in this case, they have a really high cost. Obviously, they go from 0 to 500,000 daily active user. That's quite a bit of growth. You are going to pay for that. But the kind of scale of what they ended up spending is pretty significant because Vercel has got a lot of different cost dimensions. Interestingly, they do have like a billing control where you can say, once you hit this threshold, just stop the system altogether. I don't want to pay for it anymore. But most people don't know it, and it's not on by default. So we've seen quite a few examples of companies that suddenly seen the Vercel bill blow up out of nowhere because they got some traction, they got mentioned by some celebrity or something like that. So couple of things to keep in mind when it comes to designing your systems and serverless applications, and make sure that you have something, you're building something that's very cost efficient, scalable, and whatnot. I do have a workshop coming up where I show you everything I learned about building server applications. And if you go to productionreadyservers.com, we have a early bird discount until about, I think, next week. So check it out. If you've got any questions, we've got 10 minutes, so feel free to ask any questions you want. I'm happy to answer them now or in the hallway later. But yeah, thank you very much for being here. Yeah, I hope you guys enjoy this session. Yeah, I'm not sure what's the best way to ask questions. Just, I guess, raise your hand. If no questions, just come and find me in the hall. I'm going to be around for the rest of the day. So, thank you very much, and enjoy the rest of the conference.